So what did we do the last time? Here is what we were talking about. We are trying to describe an event as seen by two observers. One will be called S, and here is the x-axis for S. Other is called S prime. S prime is sliding to the right at velocity u. Therefore, at a certain time, let me say S is me and S prime is you. When you pass me, I'm sitting at the origin of my coordinates, x equal to 0. You're at the origin of your moving coordinates, x prime equal to 0. And when we crossed each other, that time we set as 0 in our own clocks. We synchronized them. So that the event x equal to 0, x prime equal t equal to 0 also had coordinates x prime equal to 0, t prime equal to 0. When you and I crossed, we pushed our stopwatches, we synchronized our clocks, our origins coincided, and that's when it began. So after some time, you are here, this is your frame, and this is my frame. If something happens here, something could be anything. Event is, I hope you understand what an event is. That's not a relativistic notion. That's a very old notion. Something happens in some place, firecracker goes off. I ask you, when did it happen and where did it happen? And you've given the coordinates. So everything that happens is an event. You saw Elvis. I say, where did you see Elvis? At the supermarket. Okay. When did you see Elvis? I would also ask you what you were smoking, because this third question, that's not an extra coordinate, but in this case I would like. Well, I should tell you, beyond all the laughter, that's a serious issue. Why is that not a coordinate? Why not ask more and more questions and call them all coordinates? The reason the other things are not coordinates is very important. Why is time now suddenly a coordinate? Whereas you could have always asked 100 years ago, when did something happen? And the reason is that you will see in the new relativistic physics, x and t, according to one person, get mixed up into x prime and t prime of the other person. The fact that space and time coordinates can be combined to give the new space and time coordinates is why it's called a coordinate. I'll say more about it later. Now, by the way, I've posted some notes on this topic for those of you who want to have a second pass at it. I also don't know how much the textbook covers this topic, because I spend a lot of time on this topic, not in proportion to what's in the book. So you can look at those notes which are posted today. Before all the Einstein stuff, if something occurred here, you would say it's at a distance x prime from your origin. I will say it's at a distance x from my origin. This difference between our origins would be ut. Therefore, before Einstein, I would say x prime is x minus ut, and you would say x should be what you think is a coordinate plus ut. This is just going back and forth from you to me. And you can already notice that to go back and forth from you to me, we just change the sign of the velocity. Because I'm going to the right, then you're going to the left. That's why the formulas have sign of u reversed. What is the big change after Einstein? First is, I admit the possibility that maybe you will think the time elapsed since we synchronized our clocks is not necessarily the same. I leave that option open, that t and t prime are not the same. Second thing I do is, I have already explained to you that the velocity of light coming out the same for different people is very counterintuitive. Because if you're going to the right, I expect you to get a smaller speed, and yet to get the same answer. So we know that it's because we don't agree anymore on clocks and meter sticks being the same. So in particular, you will say, I don't buy your prediction that I expect to get the answer to be x minus ut. I'm going to put a fudge factor, gamma, which depends on the velocity between you and me, because your lengths are not my lengths. Likewise, I will tell you, I don't agree with your expectation that I should get x prime plus ut prime. I don't believe your lengths are really my lengths, but I'm going to put the same fudge factor, gamma. This is a very interesting result. If I think your meter sticks are short, so that I want to blow up the answer by some amount, you are allowed to say the same about me. It's one of the big paradoxes in relativity that we can accuse each other of using meter sticks which are short, and we'll go into a little bit about how that's even possible. But the postulates tell us that if my fudge factor is gamma, yours should also be the same gamma. So gamma is what we don't know. So I showed you a trick to find gamma. I said, let's imagine that this event here, which could have been a firecracker, is triggered by a light pulse that was emitted when you and I met here. The light pulse goes racing and sets off an explosion here. That's the event we're talking about. That's not a generic event. It's a particular event in which x has to be c times t, because that's the equation for a light pulse according to me. Light goes at the velocity of c. And the event has got the same velocity according to you. This event here should be connected by a light pulse that for x over t is c, and x prime over t prime is the same c. Then I said, take these two equations, multiply the left-hand side by the left-hand side, right-hand by the right-hand side, put in these numbers, and extract gamma. And I will not repeat that part. And gamma was this. Once you've got this, you can take this gamma and put it back here. Let's see what we get. So I'm going to put what we get here into this board. You guys got all of that? OK, so I'm going to put it back here, because this is just background from last lecture. What we have then is x prime is x minus ut divided by this famous square root. And if you go and solve for t prime in the other equation, it's a simple algebraic manipulation, so I don't want to waste my time doing that. You will find t prime is equal to t minus ux over c squared divided by the same square root. These are priceless. This is really all of relativity, all the funny stuff you hear about, E equals mc squared, funny clocks, the twin paradox, everything comes from these equations. And you people should be very pleased that within, 6 weeks of starting Physics 200, you have all the things you need to understand these equations, to understand where they came from. That's also a remarkable thing about relativity. A lot of the modern things in physics require a lot of mathematics. In fact, if you want to take a beam and you want to load it with weight and you want to see the stresses and strains, the math involved that is 1,000 times more difficult than this one. And yet the mathematics of relativity is very, very simple and accessible to all of you. And there is nothing that I know that you don't know as far as how to get these equations. This is what you do. Everything follows from taking these equations and analyzing them, extracting the consequences. And that's really more an issue of courage than just intelligence, because once you got these equations, you will have to take them wherever you'll have to follow them where they take you. That's what we're going to do. The rest of the whole remaining lectures are all about getting information from this equation. Now, some of you are not used to writing equations. I've noticed when you see something like this, it's not clear what is being stated. So let me remind you one more time. U is a fixed number. That's your speed relative to mine. I see something happening. I give it a pair of numbers, xt. You give the same event, another pair of numbers, x prime, t prime, and this is how they are related. So I gave you an analogy, but let me repeat the analogy. If you're now talking about the xy plane rather than the xt plane, that dot is not an event. That dot is a coordinate of a point, maybe where something is sitting. I give to it a pair of numbers x and y. Now you have a different coordinate system rotated relative to mine by some angle theta. To that same location, you measure x prime up to here and t prime from there along. I'm sorry, x prime and y prime are measured along your axis. And the formula there is x prime is x cosine theta plus y sine theta and y prime is minus x sine theta plus y cosine theta. Theta is the analog of the velocity now. If theta is 0, you and I agree completely. If theta is not 0, your axis is rotated relative to mine. And the same point has two different numbers, x, y for me, x prime, y prime for you. And the relation between them is this. So you plug in my x and y, you can get your x prime and y prime. Let me give a concrete example. Let's take theta equal to pi over 4, or 45 degrees. Then, as you know, at 45, sine and cosine, they're all the same, 1 over root 2. So in that case, x prime is x over root 2 plus y over root 2, and y prime is minus x over root 2 plus y over root 2. That's a special case when theta is 45 degrees. So for every angle, cos and sine will reduce to usual simple numbers, that happen to be a square root of 2 here. Then it tells you my x and y are related to your x prime and y prime in this manner, and you can test it. For example, take a point with coordinates 1, 1. xy is 1, 1. If xy is 1, 1, and my axis is related to yours by 45 degrees, 1, 1 lies right there. So what I expect is your y prime, there is no y prime, and the coordinate should be entirely x prime if I put in 1, 1. And indeed, you find if I put x equal to 1, y prime becomes 0. And how about x prime? It becomes 1 plus 1 over root 2. That means root 2 over root 2, which is square root of 2. And square root of 2, of course, would be the length you measure this way, because the length of the vector is square root of 2, and the vector is entirely along the x direction, so the length you will get for this coordinate will be root 2. So come back to these equations. They are the same thing. If you want, I can write x prime as x divided by this number minus u divided by this number times t. So you can think of 1 over this number here as the analog of cos theta, and u over this number as the analog of sine. So it's just that instead of cos and sine all being upstairs, some of the numbers are down, some of the numbers are up. But for a given u, these are all some numbers, constant depending on u. And x prime is a linear combination of x and t. And t prime is some other linear combination of x and t. But I should warn you that it is not an ordinary rotation. In other words, you cannot treat this as a cosine and that as a sine. They are not cosine and sine of anything. Because if they were, this square plus that square should add up to 1, and they won't. So don't even try that. This is not an ordinary rotation, but it is still what you can call a linear transformation. Linear transformation means the new numbers are related to the first powers of the old numbers. They are linear. They don't involve t squared and x squared. Okay, so that is the content of the Lorentz transformation. Everybody should understand what they do. They're a way of going back and forth. Now, you can go backwards. You can say, well, how do I write x in terms of x prime and t prime? There are two options open to you. One is, these are simultaneous equations. You got to find a way to solve for x and t in terms of x prime and t prime, and all these funny functions involving u. So treat them all as constants and juggle them around, multiply by this, divide by that. But you shouldn't do that, because you know what the answer should be. The answer should be the same as what I got with the velocity reversed. So x will be x prime plus u t prime over the square root. If I write the square root, it means I don't feel like putting what's in it. It's the same old thing. So I got tired of writing that. T prime will be t plus ux over c squared divided by square root. So one should be able to go back and forth. Just like in this formula, if you like, I gave it to you as an example long back as a homework problem. You can write a new formula that says x is equal to x prime cosine theta minus y sine theta, and y prime is equal to something, I mean, y is equal to something, something. And the way to get that is to either solve the equations or realize that if I go from me to you by a theta, I go from you to me by minus theta. And all you have to do is change sine theta to minus sine theta and leave the cosine theta alone. Similarly here, you change the sign of the velocity u to get the reverse transformations. Okay, so that is the Lorentz transformation. Now we are going to start milking the transformation. Everything is going to be applying it to understand various things. The first step in getting the mileage out of the Lorentz transformation is to take a pair of events. I urge you, whenever you get a problem in relativity, to think in terms of events, and quite often think in terms of pair of events, two events. So event one is, let me give concrete events. And most of the relativistic examples involve some degree of violence. And so this one involves a gun. So I will take this gun. So I'm not going to point at any of you guys. I fire the gun. That's event one. Then bullet hits the wall. That's event two. You can take two events connected by a bullet leaving me and hitting the wall. Or you can take two events not connected to anything. Okay? You can take two unrelated events. But it doesn't matter. We're going to call them event one and event two. So event one will have coordinates x1, t1, right? And according to you, x1 prime, t1 prime. So write a Lorentz transformation that first relates x1 prime is x1 minus u t1 over the square root. Then right here, t1 prime is t1 minus u x1 over c squared divided by the square root. Similarly, take the second event and write the law for that. Well, it's the same thing with the new numbers in it. So t2 prime is equal to t2 minus u x2 over c squared divided by square root. Now take the difference of 2 minus 1. You can take 1 minus 2, but it's very common to define the difference to be 2 minus 1. And call it delta x2 prime. Delta x2 prime is identical to delta x prime is x2 prime minus x1 prime. All the deltas will be defined to be second minus the first. I'm telling you to take x1 prime subtracted from x2 prime on the left-hand side and call it delta of x prime. Delta of x prime is the difference in the spatial coordinates of the two events according to you. If you come to the right-hand side, now this is something you guys should be able to do in your head. I want to subtract that from that. They share the same denominator. So let me put the denominator there. In the numerator, you will get x2 minus x1, which in my convention, I will call it delta x, and the other one will be u delta t. What this tells you is that differences in coordinates also obey the same Lorentz transformation. Instead of saying the coordinate of an event was xt, and you get x prime t prime from the Lorentz transformation, if you take a pair of events, and they are separated in space by delta x and in time by delta t according to me, the separation according to you, your delta x primes and delta t primes are given by similar formulas as the Lorentz transformation. Put a delta everywhere. This just came from taking the difference of two equations applied to the two separate events. All right. You can also do this backwards if you like. If you want the differences that I get in terms of yours and yours in terms of mine, you have to reverse the sign of u. So I won't do that again. Yep.
Where you have t prime under the, yeah, shouldn't that be t equals t prime?
Here?
Yeah, not a vision.
This was the formula for x in terms of x prime and t prime, and t prime in terms of t and x. Here? Okay, I got to give some numbers. This is A. This is B. This is C. Where is the problem? One of you.
A and C too.
A.
To the right of C.
Oh.
You wrote 10 times.
Oh, yes, yes, yes. Of course. Yes. Thank you. Okay, now public apology is forthcoming. You want me to do this? Yes? Thank you very much. Okay. Do not hesitate to do this. Okay? In fact, when I said, I don't know any more than you do about this, it looks like I know less than you do about this. So the fact that I know this doesn't mean I'm going to get it right. So all of you screwed up in the midterm, remember there is hope for you. Maybe you won't do well as students, but you can become a professor here. Because apparently, it's all right for us to get things wrong. That's correct. Very good. Okay, so if you're following me that well, I'm very happy now to know you must be following what I'm saying here. So now let us, everything, now I keep telling you I'm building it up in a big way, but everything really is going to come from this version of the Lorentz transformation for differences. Look, suppose you were smart enough like Einstein and you deduce these equations for gamma, what do you do next? You write them down, you can publish them and say, according to me, this is the rule for transformation. But you cannot stop now. You have to say, what are the implications of my equations? Because these equations are dramatic variations of Newtonian laws. For example, let's just do one thing. Two events are separated by 10 meters according to me. Delta x prime, if delta x is 10 meters, delta x prime is not 10 meters. It's 10 minus something divided by something. So the distance between two events is changing. That's not supposed to happen just because you get into a train. Right? If I hold my hands and say, I caught a fish that big, that distance should be same for me in the train, or if you look at me bragging in the train from outside the train, you should find the same distance. We're saying it's not true. Likewise, if I say two events took place, I came to Yale on a certain day, I got a degree 4 years later, that's supposed to be true for anybody. But that's also not true. If delta t is 4 years, delta x is whatever you like. Maybe you never left New Haven, so delta x is 0. That's 4 years, that's not 4 years. These are all drastic consequences, and we're going to explore the consequences. The first thing I'm going to do is to make sure that the velocity transformations from one frame to other obey the requirements we set on them. So here's what I'm going to do. Event 1, I fire the gun. Okay? Let me just call it event 1, I fire the gun. Event 2, a bullet hits the wall. So the separation between these two events is delta x for me, and the time it took the bullet is delta t. You can also see the bullet from your train, and you think the distance between me and the wall is something, and the time between the firing and hitting the wall is something else. Then what's the velocity of the bullet according to you and me? V is velocity of bullet for me would be delta x over delta t. Okay, now I should be a little more careful with my notation. Usually deltas are used for infinitesimal numbers. Especially when you're going to define a velocity, velocity is the limit of these guys going to 0. But it's a property of Lorentz transformation that at this level, when I say differences in time and differences in space, they are not necessarily small. Nowhere was I assuming that the difference in x was small or difference in t is small. They could be even separated by 5 light years. You can still use them. So at this stage, don't think delta x has to be infinitesimal. It is simply a shorthand for difference. If I had all the time in the world, I would write everything as x2 minus x1. But I'm using delta as a shorthand. But when I'm going to find the velocity of a bullet, which could even be the instantaneous velocity, then here I do want to take the limit in which they go to 0, so it becomes dx dt. So from now on, for this purpose of velocity calculation, you should take them to be infinitesimal and approaching 0, but not in general. These equations are valid for arbitrarily big intervals in time and space. Now, W, let it be the velocity for you. That is, I am S and you are S prime. W is delta x prime over delta t prime with suitable limits. Well, from these transformational laws, you can get them. Because here is delta x prime, and here is delta t prime. Let me divide this by this on the left-hand side to get W. When I write delta x prime over delta t prime, you guys take the limits of everything going to 0. I don't feel like writing that. In fact, it's true even without the limit, but let's apply it in the end to instantaneous velocity. Then what happens on the right-hand side? Here is what delta x prime is equal to. Can you do this in your head? It is delta x minus u delta t. This denominator cancels between dividing this by this. So it looks like I just divided this guy by this guy, because that's when you divide the left-hand side by the left-hand side, you have to divide the right-hand side by the right-hand side. Now you should have an idea of what I'm planning to do. What do we do next to this expression here? Yes? Limit of what? If I just take the limit of delta t going to 0, you're just going to get 0. That's not the limit you want to take. You've got to bring velocities into the picture. Yes?
As u approaches c.
Pardon me?
As u approaches c.
No, for any value of u.
Everything by delta t.
Yes. What you want to do now is to divide the top and bottom of this by delta t, because you got the velocity of the bullet according to you. I want to get the velocity of the bullet according to me into the picture. That is delta x over delta t. Well, this is not a typical derivative in calculus. Okay? You got to divide everything by delta t. Then you will get delta x over delta t there minus u divided by 1 minus u over c squared times delta x over delta t. This is true even for finite differences. Now take the limit. Then this becomes the velocity of the bullet minus u divided by 1 minus u v over c squared. So you got to draw a box around this guy. This is another great formula. So I hope you know why I divided by delta t. I want to find the velocity of the bullet according to you and according to me. For you, I took the distance over time. Well, I've got all these distances and times in the top and bottom, so I divide by the time, so everything turns into a velocity. So this is the velocity of the bullet according to me. If you're going to the right at a speed u, in the good old days, what did I expect? You got to understand that. My expectation in the old days would be v minus u. Right? Bullets going at speed v, you're going at speed u to the right, so you will see a diminished speed by an amount equal to your speed. But now is the twist. There's something in the bottom, and the stuff in the bottom is a number less than 1, because it's 1 minus something. We're going to jack up velocity. Therefore, the velocity you will actually measure is somewhat bigger than what I expected in the old days. If you ever want to get back to the good old days in any relativistic calculation, you should let the velocity of light go to infinity. Of course, it's not infinity. What you really mean is u over c and v over c are negligible. That means my velocity, the bullet velocity, they're all small compared to the velocity of light. We get back the answer from the old days. This is the answer from the new days. Now let's find the beauty of this result. Let's get the reverse result. Let us solve for the velocity I get in terms of the velocity you get. Now again, I think you realize you can do the algebra, but you guys should know that to go from me back to you, I should simply reverse the sign of our relative velocity. This is the backwards result. In other words, you're in a train, and you fire a bullet towards the front of the train. What speed do I attribute to the bullet from the ground? Well, I add the bullet speed to the train speed. That's what the numerator is. Denominator says the answer is somewhat less than that, but by this number. Yes?
The denominator, would it still be uv over c squared, or would it become uw?
Thank you very much. Yeah. I mean, that's absolutely correct. What I really need to do is quite correct. It's not simply to change u to minus u, but to change the velocities that you were seeing and put them in the place of velocities that I was seeing. That's correct. This is what you want to get. Now, let's look at the strength of this result. If someone tells you, according to relativity, nothing can go faster than the speed of light, you can try to beat the system as follows. You can come to me and say, can there be a gun whose bullets go at 3/4 the velocity of light? And I will say, yes. And you'll say, how about a train that goes at 3/4 the velocity of light? And I'll say, that seems to be allowed. Then you can say, well, let me get into this train at 3/4 the velocity of light and fire a bullet at 3/4 the velocity. Then from the ground, it should appear to be going at 1.5 times the velocity of light. Well, that's the naive expectation. But if you do it now, let's put w equal to 3/4 c and u equal to 3/4 c. The old answer is disaster. It says 1.5 c. But the correct answer is that plus 3/4 squared. So what is this guy? This is 1.5 c divided by 1 plus 9 over 16. If you multiply everything by 16, on the top you'll get 24, the bottom you'll get 25c. You see, you can jack up the velocity as seen by the ground, but it'll never be 1.5. It'll still be less than the velocity of light. And the last thing you want to check of this velocity addition formula is why we started the whole thing. In other words, suppose I see a pulse of light. Let's go back now to this formula. W is v minus u over 1 minus uv over c squared. Rather than applying it to a bullet or whatnot, let's apply it to the light pulse itself. So I saw a light pulse. So I say the object I saw, which is what v stands for, had a value c. And this is the pre-Einstein expectation. W should be c minus u, because the pulse will appear to travel slower to a person moving in the same direction as the pulse. But our new formula says it is really that times u times c over c squared. So let's cancel 1 power of c, multiply top and bottom by c, and you will find it as c. So the velocity of light will always come out to be the same. That was built into the formulas, but it's a good thing to test. So what you find is velocities don't add in the simple way. If they did, you are in trouble. You cannot get an upper limit if they add it in the simple way, because you can put a rocket inside another rocket and add up all the speeds, and even though each one is less than c, the total could be whatever you like. But they don't add that way. They add this way, so that the answer is either bigger than what you think if v and u are opposite, or smaller than what you think if the velocities in the top are of the same sign. No matter what you do, the answer will always be less than c. Okay, so that is the first conclusion from this. Second conclusion, which is again very staggering, is that simultaneity is a relative concept. In other words, if two events occur at the same time for me, they don't occur at the same time for you. That's very surprising. For example, if you have twins born, twins cannot be born in New York and Los Angeles. So I got to take two kids of different motherhood, just happen to be born at the same time. When I say time, we're not talking about trivial 3-hour time difference between Los Angeles and New York. That's an artificial thing. In the Einstein world, you imagine we all have clocks that read the same time. So by that measure, two kids are born at the same time. But if you watch that from a moving train or moving rocket, you will disagree on that. You will in fact say they are not simultaneous. How does that come? It just comes from going to this formula. Delta t prime is delta t minus u delta x over c squared divided by this number. And all I'm telling you is, even though delta t is 0, delta t prime is not 0. Another shock. Simultaneity is not absolute. We used to think it's absolute. In other words, two events occurring in Los Angeles and New York, they can be arranged to be simultaneous for me, living on the planet, let's say, but if you go in a rocket, I expect you to agree they were simultaneous. I mean, how can it be different? Two things are happening right now at different places. It's got to be right now for you. But it's not. It just comes from that formula. Once again, if the velocity of light is made much bigger than everything in the problem, simply just set it to infinity, you will find delta t prime is delta t. That goes back to Galilean times, or the old pre-Einstein times. That's why in relativity, space and time form a new space-time, and time is called the fourth component, because if c goes to infinity, delta prime is always delta t, and t prime is always t. That coordinate never mixes with anything else. It doesn't deserve to be called a coordinate. Whereas the x and y coordinates, they mix into each other when you do rotations. After Einstein, the space and time coordinates mix with each other to give you new space and time coordinates under Lorentz transformations, which means when seen in a moving frame. That's why time is now elevated to another dimension, because it transforms very much the way x and y did. The details of the transformation are different. You have sines and cosines replaced by u and u over the square root, but it's still mathematically the way components of vectors will transform. Okay, so simultaneity is relative. So you have to ask yourself, how did that happen? So here is a famous example that is given in all the books. Maybe it was given by Einstein. I'm not sure. So here is a train. Let's say the train is at rest, and you're standing in the middle, and you want to arrange for two events to be simultaneous. Oh, by the way, there is one catch. If the two events occurred at the same time and the same place, delta x is 0, delta t is 0, then the transformation will tell you delta x prime is 0 and delta t prime is 0. Because two events occurring at the same time at the same place means, for example, my two hands came and clapped. The two hands were at the same time at the same place. If someone said, well, they were not at the same place at the same time, it means I did not clap. Or two cars collide. So if two things occur at the same time at the same place, something happened that they met in space-time. You cannot find another observer who says they did not meet in space-time, or they will say the two cars did not collide. So relativity, even after relativity, it is true that two events at the same time and same place occur at same time and same place for all people. Same time alone is not enough, and same place alone is not enough. Do you see that? If two cars came and they collided, they were at the same time at the same place. If the cars were at the same time, here and there, that's no accident. If they were at the same place, because this car went and 2 minutes later that car went to the same place, nothing happens. Right? That's why you say this poor guy was in the wrong place at the wrong time. You don't say this guy was at the wrong place. What does that mean? You can go to the Battle of Gettysburg site and stand now, nothing happens to you because it's the same place, but it's the wrong time. Okay? We all realize same place, same time is a congruence in space-time. And even after Einstein, you cannot say something did not happen. Okay? We'll leave that to politicians. These did happen. These did happen, and the equations have the property. But I'm considering events separated in space, but at the same time. So you're in the train. Your job is to make two things happen at the same time. And here's what you do. You send a beam of light that splits into a, here's a blown up picture. Beam of light comes and splits like that and goes to the back and front of the train. You're in the middle of the train, and you know that events will be simultaneous for you. The pulse travels on either side and hits the two things at the two ends, sets off two explosions, and you have done the best you can to have simultaneous events. Okay, now I see you from the ground. So all this happening in the moving train. And you have every right to say you're not moving. But to me, relative to me, you're moving. That's a fact. And I look at how well you did with this. So you sent off these 2 light pulses. Then what happened? This wall of the train is moving away from the light pulse. This wall of the train, the rear end, is rushing to meet the light pulse. Now, the velocity of light is the same for everybody, so I can think in terms of what happens. If one wall is rushing to meet the light pulse and one wall is running away from the light pulse, I know very clearly the firecracker in the back of the train will go off first and in the front of the train will go off later. That means the delta t will not be 0. In fact, you can see delta t will be negative because the event with the greater x coordinate occurs later. And that's also an agreement with the formula. If delta t is 0, delta x prime will be some negative number. Now, why do we bring in the light pulse? We bring in the light pulse because we can tell that they will simply will not be simultaneous, because about the light we know this. Its velocity is same for everybody. That's why all arguments in relativity involve doing things with light pulses or communicating with a light pulse, because we know what light does. It travels at one and the same velocity for all people. That's the postulate. Therefore, we know you couldn't have done any better in making them simultaneous, and I simply disagree with you. I'd say they just did not happen at the same time, and there's no question of who is right. Operationally, for me, those 2 events were separated in time by some amount, and for you, they were not. That's a great new idea, that things did not happen at the same time for all people. And relativity tells you that they didn't and tells you by how much they will differ. Okay, then I take the next surprise here. Next surprise has to do with clocks. The claim is that clocks will not run at the same rate. Okay, when we bought the clocks, we compared them, we got them from the same shop. They were completely in sync, and you put one in your train and you got into your train. And the claim is that I will find that your clocks are running slow. Let me show that to you. Again, if you want to do anything in relativity, at least learn this one thing. Go back to Lorentz transformation and think in terms of events. Then it's just going to come out of the wash. If you try something original on your own, you people do all kinds of stuff. I've seen you going into cyclical, circular arguments from which you cannot even come out till somebody rescues you. So don't do that. So I'm looking at a clock. You've got to ask yourself, how do I turn this issue of time into a pair of events? So I have my clock. So it goes tick tock, tick tock. So I take 2 events. Event 1, clock says tick. And event 2, clock says tock. I tell you why I have tick and tock, because I want to have 2 distinct kind of events, so we can talk about them. So this event is a clock that I am carrying with me. Clock is with me. So let me put the clock at the center of my coordinate system, at the origin. It doesn't matter where it is. Let me put it at the origin. The space-time coordinate is x equal to 0, t equal to 0, is the first tick of the clock. How about the next tick? The next tick, this is x and t coordinates. The tock of the clock, let me call tau 0 is the time of the clock, is the time period. How many seconds elapse between the tick and the tock? Main question is, what is the location of the second tick or the tock? Where does that happen? Yes? It doesn't move with respect to me, and I'm talking about the clock that I'm holding in my hand. So if the first event took place at x equal to 0, second one also takes place at x equal to 0. You understand? I'm holding the clock. I've traveled forward in time. It's tau 0 seconds later, but the clock has not gone anywhere. So the 2 events, the 2 tickings of the clock, are separated in space by 0 and in time by tau 0. That means delta x is equal to 0, delta t is equal to tau 0. What do you get? According to you, the time difference between the 2 ticks is delta t, which is tau 0, minus u, etc., times 0 divided by this factor. That means the time difference between the 2 ticks will be bigger. If tau 0 is 1 second, If you divide 1 by 1 minus u squared over c squared, you're going to find out it is less. It's more. For example, if this factor in the denominator is 0.5, then delta t will be 2 times tau 0. In other words, when your clock has taken 1 second to go from one tick to the next, I will say, according to me, the real time elapsed is 2 seconds. It can be 10 seconds, it can be 100 seconds. You can make delta t as big as you like by letting u approach c.
Do you actually mean t prime or?
Yes. Thank you. I'm having this problem today with the prime. T prime is tau 0 over this. If you put tau 0 equal to 1 second, question there, guys?
I wanted to know why that u went to 0 for the...
No, u did not go to 0. U is not 0. U delta x over c squared is the delta x that went to 0. Go to the Lorentz transformation. Delta t prime is delta t minus u delta x over c squared. Delta x is 0.
Okay.
Because that's where I'm telling the equation the clock is at rest with respect to me. That means the two.
That referred to the observer moving relative to you.
No. In this example, let the unprimed observer be the one holding the clock.
Okay.
Then delta x is 0, delta t is whatever the time of the clock is, 1 second. Delta t prime is seen by anybody else going at a speed u relative to me. You can also do it backwards by taking the clock in the hands of the s prime. You've got to do a little more work. It's a lot easier here because I get to pump into the equation two facts at one shot. That the time between the two ticks is 1 second, and it's at rest with respect to me, which is why the delta x vanished between the two ticks. If I want to use your equations, delta x prime won't be 0 because the clock has moved. And you can do it. I think shown in my notes how to do that, but it's unnecessary. This is the main result. Now here is the paradox. You can go back to the backwards equations. Let's do this informally, okay? Let's not write it again. It will look like this, right? We know that. Let's take a clock, your caddy, which ticks off 1 second. So between the tick and the next tick, the time difference is 1 second, space difference is 0. I'll find delta t is 1 over a square root. So I will say your clock is slow, you will say my clock is slow. How is that possible? How can it be that we accuse each other of having, yes?
Because the person in the train can just equally say that the other observer is moving with...
Oh, you're absolutely right. The predictions are in agreement with that principle, but I ask you to think about the conflict you have. Yes?
There's an analogy with visual perspective in that two people who are far away from each other view each other as being...
Oh, that's
slower
very
than
good.
they would be when they're close up. And that doesn't bring into any...
No, that is correct. Let me repeat what he said. He said if there are two people, when they're right next to each other, they're at the same height. And they move apart, and each person looks at the other person and finds the person diminished in size because of the distance. And each person can tell the other person, you look small from where I am. In fact, even more paradoxical is how in this world, two people can simultaneously look down on each other. You figure that out, right? There are two people who simultaneously have higher opinion of themselves or the other person, and at the same thing, they look down on each other. I have not found out how many space dimensions I should embed these people to make that possible. But this is certainly correct, that spatial resolution does give the impression. So here's the answer that's usually given to explain this to you. If I take a real clock like this watch here, and I ask you, why does it look slow to you when I'm moving relative to you? It's difficult because it's got, electronics and stuff, and I still don't know how to set the clock on my VCR. I'm not going to figure that out. So for all of us guys who are challenged, there is a clock that's particularly simple. And the clock works like this. It has got two mirrors and a light pulse just goes up and down between the mirrors, and every time it completes a round trip, it sets off some detector and it goes click. Now, this is very important to mention that this is my x coordinate and that's the y coordinate. And I did not show you here. There are logical arguments on why, if you and I are moving along x, our y coordinates, if they agree in the beginning, continue to agree. That's because if you say something is 2 meters tall and they pass each other, you cannot have a disagreement on the fact that heights are the same. Whereas in the linear dimension, there is room for discussion. In the transverse dimension, there isn't. So anyway, I have this clock that goes up and down. Light pulse goes up and down. It goes a certain distance L in the vertical direction, and 2L over C is the time period of my clock. That's the time for a round trip. You look at my clock, and what do you think is happening? Remember, you are moving to the right relative to me. So according to you, my clock is moving to the left, and it looks like this. Light beam is going on a zigzag path according to you. You agree? That's very clear. If for me the pulse is going up and down, for you it's going on the hypotenuse. You can imagine how with the hypotenuse u squared and c squared are going to come from drawing the sides of the triangle. That's why the time will come out longer. Now, why do we like this clock? Because we know everything about the operation of the clock. We know that this path is longer than the straight up and down path because the transverse coordinate is known to us. Furthermore, we know the velocity of light is the same in all frames of reference, so light going on a longer path is simply going to take longer. So I know your clock would slow down. Now here is the beauty. The beauty is that if you have a clock that's going up and down, straight up and down, when I see it, it's going to look like this. So it's as simple as saying that if you had these two clocks, when I think it's going up and down, you think it's a zigzag this way, and I look at your clock, it's a zigzag the other way. It's perfectly okay for me to say to you, your light pulse is going on the hypotenuse, mine is going up and down, and why you can say that to me. So at least this light clock explains to you why clocks will appear to be slow. Now the question you can ask is, what if I have some other clock with gears and wheels and teeth and whatnot? How does that slow down? The answer is we don't know exactly how to explain that clock, but I know that if you carry a light clock and another clock made of wheels and gears, they should run at the same rate. They should run at the same rate because if they ran at different rates, one slowed down and one didn't, by comparing the two clocks, you can determine your velocity. And that we know is impossible by the postulate that you cannot detect uniform velocity. Therefore, if the light clock does something, all clocks must do the same thing, regardless of their mechanism. And that includes biological clocks. So if you have a clock, which is just yourself, I look at you, over 15 or 20 years, I notice some changes. You become taller, then your hair turns white, your teeth fall off. That's a clock. And that clock should also slow down, because I don't care how your life systems work, but you are a clock, and you got to slow down. That's why you can make predictions about what will happen to living systems, even though that's not our main business. So in particular, if you take a clock, which is made up of mechanical parts, and a human being, and they travel at high speeds, the aging of the human being should slow down, just like the clock's ticking will slow down, without knowing the reasons for it. So this leads to a very famous paradox called the twin paradox. So the twin paradox says that you got two guys, twins. Now, this is actually a valid example. They're born at the same time, same place, and then one goes on a trip at some speed u and goes around and comes back. So I think the person's been gone for 20 years, my twin. So let's say he was 20 when he left, so I expect him to be 40 when he gets back. But he'll come back younger because as a clock, he has slowed down. So what I think is 20 years could be, my time is 20 years, but his time could be 10 because this factor downstairs is 0.5. So he can come back being younger than me. Yes?
Doesn't that paradox arise in general because the time dilation stuff is because of acceleration and not because you have the different velocities?
But we got to be careful. So his point it has something to do with acceleration. But the real question is this. So if I'm on the ground and I send my twin on the trip and we meet, Now the clocks are being compared. As long as the zigzag is going this way and that zigzag is going that way, you can say what you like. But what if the clocks are brought head to head and compared? Can they both be slower than the other? We know that's impossible. So instead of clocks, we use human beings and dramatize a paradox and say, who will be younger, me or the twin who went on the rocket? Well, there can only one answer that question. And yet, what if the twin says, well, I have no reason to believe that I moved. You're the one who went on the trip the opposite way, so you got to be younger than me. Yes?
I guess the case that the twin knows that he's the one that moves because he felt all the effects of the acceleration that necessarily had to bring him back to the circle. He can't just travel along a straight line and not accelerate and then meet the twin back where...
Very good. Okay, I couldn't have said it better. Let me repeat it. The point is, as long as you've got oppositely moving clocks, they can believe what they want of each other. But if you want the clocks to be subject to a comparison, then you can never compare objects that are constantly moving at opposite velocities. So somebody's got to turn around and come back. So in the case of the twin, he and I were at rest. The twin got into the rocket to set up the velocity difference between him and me. So in the early stages, he's the one undergoing acceleration and not me. And likewise, the twin went somewhere and stopped and turned around and came back. The twin is suffering the deceleration. So there are two periods at least during the voyage when the twin has no right to claim that he is not moving, that I am. That's why we don't have the same status. Whereas for me, the whole time, Newton's laws and the laws of inertia were operative for me. Whereas for him on the rocket, during takeoff, things started flying off, and during landing, things started flying off. He cannot possibly claim he has the same status as me. That's why in that problem, the relationship is not symmetrical. And one person can say, I did not move because I was always inertial. Other will say, have to concede that he moved. Yes?
What if our first twin moves, accelerates, and then the other one accelerates to the same speed?
Yeah, then if you do it, if you give them symmetrical accelerations, both leave like this and both come back, then both will agree on their age, but they will disagree with the person on the ground. Suppose there's triplets. You got triplets and two kids are sent out that way, third one stays back. The third one that stays back will be older than the others. So this is not science fiction at all. If you want to be alive for the year 3000, you can do it. You just have to get into a rocket at sufficient velocity close to the speed of light so that this is 3000 years, okay? And you figure out how long you got to live, maybe another 50 years. Do the math, you find the speed, get into the rocket, and go and come back. Now, this experiment is done all the time with microscopic particles. You know, they are accelerated in Fermi lab, for example. They go around on a ring, and just by virtue of their motion, they live a very long time. So particles that are supposed to have a short lifetime, which you calculate in their own rest frame, live much longer because they're moving. And one way to keep them moving is to put them on an accelerated ring, and they live for a very long time. Yes?
But the guy on the rocket, respect to the rocket itself, it's still 50 years, right? Not 3,000.
No, no, rocket will think I'm 50 years older. If you went on the rocket, it's 50 years for you. For people on the ground, it's 3,000 years.
Right, so you still live 50 years on the rocket.
Yeah, but if you don't want to age at all, you can arrange it. You want what, 5 years? Okay, you just fix the number. You want to age only 0.5 years? That's another number. You never run out of numbers. You can let U approach C as much as you like. And you can live as long as you want. And come back whenever you want. Other issues like going backwards in time, I'll come back to that later. There are problems with that. We'll come to that. But you can stop time as far as we know, and we see it all the time. Muons are produced in the upper atmosphere. Their lifetime is something 10 to the minus 6 seconds or whatever. Even if they travel the speed of light, c times that time is not long enough to cross the atmosphere, but they make it here. How do they make it? They make it because their lifetime is computed in their frame of reference. They still think they lived only their lifetime, but I think they lived a much longer time. That's how they made it to the Earth. But how about from their point of view? They only lived a short time, and how did they go the 100 kilometers? That's the next thing I'm going to tell you. According to them, the atmosphere is not 100 kilometers, but maybe 8 kilometers long. And that's the last point, which has to do with the length contraction. So length contraction says, by the way, so the thing to remember about time dilatation is every clock runs the fastest in its own rest frame. In any other frame of reference in which the clock has any velocity, it will appear to be slower than the advertised time period of that clock. Okay, last thing I want to do is length contraction. Length contraction says if you have a meter stick, and you and I bought them from the same store, once you're in this plane, or in this rocket, I will claim your meter sticks are actually shorter than a meter. In fact, the shortening factor is this. This is the shortening factor. In fact, way back in the derivation of the Lorentz transformation, the fudge factor I calculated, taking your lengths into my lengths, is precisely connected to this factor. If you say the length is something, I will tell you that the length is actually less than that, because your meter sticks are short. But let me prove that to you. So let's take a rod that's moving. It's moving at a speed u. You're carrying the rod. And I want to find its length. What should I do? That's the question. Okay? So rod is moving at speed u, and I want to find its length. So delta x prime is delta x minus u delta t over the square root. I'm going to make a pair of events to find the length of the rod. Event 1, remember this rod is zooming past me. Event 1 is when this front end of the rod hits a certain marking on the meter, on my graduated x-axis. And event 2 is when the back end of the train hits my origin. And the distance between those two is the length of the rod, provided one condition. How do you find the length of a moving rod? You find this end and that end at the same time. Otherwise, you will screw up, right? If you find this end now, go on a lunch break and come back when the rod is over there and say that's the rear end of the rod. You get that to be the length. That's not how you find the length of a moving object. You find the length by measuring the coordinates of the two ends at the same time. Consequently, the same time means delta t must be 0. Delta L is delta x is the length according to you. According to the person going with the rod, the two events, since they take place at the two ends of the rod, are separated by the length of the rod, because the rod, according to you, is not going anywhere. Suppose you have a rod. It's not moving relative to you. Something happens at one end, something happens at the other end. What's the spatial distance between them? It's the length of the rod. That's the meaning of the length of the rod. Therefore, if you cross multiply, you get this result. L is L0 times. So the real length. So a rod will appear longest in its rest frame, and to anybody else it will appear shorter. Clocks appear fastest in the rest frame, rods appear longest in the rest frame. For anybody to whom a rod is moving, the rod appears short. So here is another paradox then. I make a hole in my x-axis. I make the hole to be half a meter long. This is half a meter. You and I bought a meter stick, but you're moving at a velocity where this number has become half. U over c is 1 over root 2, so u squared over c squared is whatever. Look, it's whatever it takes to make this factor half. So I expect your meter stick to have shrunk to half its length. So I make a hole on the table, half a meter long, the rod goes by, I think it will fall into the hole. That's my expectation. You come and say, my meter stick is a meter stick. The hole that you dug, that you think is half a meter long, actually quarter meter long. So there's no way my meter stick is going through that hole in the table, because it's 4 times as long as the hole in the table. You understand that? Normally, you make a meter stick, you put it on top of a hole of the same length, it will fall down. But if it's a moving meter stick, which has contracted, according to me, from 1 meter to half a meter hole is enough for it to fall. But from your vantage point, my half a meter hole looks like a quarter of a meter hole. Your meter stick still looks like a meter. So the question is, when this experiment occurs, will it fall or not? Again, these are all paradoxes. If you invented the theory, you got to defend these paradoxes. You cannot get two answers to one question. That's the logical issue. So the answer to these problems is, if you know one point of view in which it is correct, that's the right answer. Then the other person has to figure out what happened. So from my point of view, if I made a 1/2 meter hole and your rod is shrunk to half the length, it's going to fall. So it will fall. The question is, how does the other person reconcile himself to the fact that here is, according to that person, the hole is a 1/4 meter long and the rod is 1 meter long. Well, for it to fall, you got to give it a little tilt, okay, so that it can actually fall in. I give it a little tilt here. How can this object fall into that end? The way other person explains it is, he said first this end went in here, other end was sticking way out. Then sometime later, the second end went in here, and that's how I got through the hole. Namely, the two ends did not go at the same time. That way, it's certainly possible for a 1 meter stick to go through a 1/4 centimeter hole in the table. I mean, give the rod a little tilt so it can fall into the hole. The tip enters first, the tail is way outside. Then after a while, the tail goes in. And in that manner, the rod goes in. So they can reconcile this paradox by saying the two ends did not go at the same time. Also, if you ask the other person who thinks something is 2 meters long and the other person thinks it's 1/2 meter long, how do they reconcile it? I say I measured the two ends at the same time, but you will tell me you did not measure the ends of my meter stick at the same time. You measured one end and you goofed off, then you came back and measured the second end. By the time the rod had slipped to the right, you measured that end and you goofed off. You wait till it came there, then you measured the other end. That's why you got 1/2 instead of 1. And nobody is right or wrong. I did measure the two ends simultaneously according to me, but you don't have to agree they were simultaneous. So it's by going soft on what simultaneity means that you're able to reconcile this. In the Newtonian days, simultaneity is absolute, length was absolute. In relativity, simultaneity is relative and length is also relative, because the operational way to find the length of a body will not satisfy all observers. If I find the length of your moving meter stick, the two ends at the same time, you will say I didn't measure them at the same time, and the formulas of relativity allow that. That's how we live with the fact that we accuse each other of having relatively short meter sticks. I blame you on your measurement, but that blame is not a genuine blame, because you can dig a hole equal to the reduced length and things will fall in. So you have every right to say things have shrunk. And I will say, I didn't shrink, I fell in because my nose went in first and then a little later the tail went. There are various paradoxes. I'll just leave you with one. You have a garage, your parents built your garage 12 meters long, you bought a car 14 meters long, can you park it? Well, if you go at sufficiently high velocities, so the 14 gets shrunk to 12, there'll be a brief instant in which both ends of your car are inside the garage. Okay? Of course, you will have to smash through the back end of the garage, but you will maintain, yes, I smashed in that, but my car was in the garage for some time. And the parent will say, no, the front end went in, smashed the rear, the back hadn't even come in, a little later the back came in. So everyone will agree, you broke the garage, you broke the car, and the lengths were contracted relative to each other. And the phenomenon is that, according to you, there was a time the whole car was in the garage, and according to the parents, it was not.